All right, this is section 10.4 on Ampere's law. Ampere's law is the second of the four Maxwell's equations. Maxwell's equations, what they are, there are four equations that unite electricity and magnetism into one field of study called electromagnetism. We've done one, which was Gauss's law. Now there's also a Gauss's law for magnetism. It's probably the least important of Maxwell's equations. It just says that the magnetic flux through a closed surface is zero because there can't be a magnetic dipole. Now, the analogy to Gauss's law in magnetism is Ampere's law. So that's a bit weird. So Gauss's law, it was used to find the electric field due to a charged surface. Ampere's law is going to be used to find the magnetic field due to a conductor. And the way that it does so is very similar to Gauss's law. So we're going to get into 10.4. We'll start off and look at what Gauss's law was. We can see what we're going to do with Ampere's law, and then we'll get into the derivation. So with that, let's go ahead and do 10.4. So here's Gauss's law. To recap what Gauss's law was, it was a way to find the electric field due to a charged object. And the way we were able to do that was we used the properties of an imaginary surface. This imaginary surface is called a Gaussian surface. It's not actually there, but this charged object right here creates a field, and that field has a flux, an electric flux through the surface. And we use properties of the surface and the flux through the surface to drive the electric field. Now we had this really scary integral right here, but we never actually really did much calculus because when you have this integral, the field was constant. We chose the Gaussian surface with symmetry such that the field was constant, so we always pulled that out of the integral. And then our integral of dA, well, we had a surface, a 3D surface, where we just did the surface area instead of actually doing calculus. Then we also have the charge enclosed here. Now it's important to understand Gauss's law because basically with Ampere's law, we're essentially going to do something very, very, very similar. We're going to use an imaginary region. This is going to be a 2D region, and we're going to use properties of that to derive the magnetic field. To derive Ampere's law, we're going to consider this current carrying wire here. And around this current carrying wire, we're going to have a loop. Now, this is not a loop of wire. It's just simply a loop. It's an imaginary loop. Nothing's actually there in this loop. And what we're going to do, we're going to look at this integral right here. This is a line integral. This means the integral over the closed loop of the field vector, and that's the field through this loop right here, dot dl. And we can use the right-hand rule to find the direction of the field in this little loop we're drawing. So we know what B is. That's the magnetic field. dl is going to be small pieces of this loop. Now, this is in contrast to the Biot-Savart law. In the Biot-Savart law, the dLs were small pieces of the current carrying wire. These dLs here are not part of the wire. They're part of just this loop going around the wire. And again, this loop around the wire is not really anything. It's just a loop. We're going to use properties of this loop in order to derive Ampere's law. So we'll go to the derivation, and I'm going to go ahead and do that on the iPad. So here we are at the derivation. So we have the integral of the closed loop of B dot dl, and these are both vectors. Let's look at what these vectors are. And these are going to be both going around this loop here. So we have a current carrying wire. That's actually there. We actually have a current carrying wire. This loop that we drew, it's imaginary. This has kind of two names you can call it. It's called either an Amperian loop, named after Ampere. It's also sometimes called an Amperian path. Either way, it is always going to have to be a closed loop. But you'll see both names in the book or wherever you're looking at. So for our two vectors going around the loop, we have the magnetic field B. So the direction of the field using the right-hand rule. So you take your right hand, you put your thumb in the direction of current, which is into the page. Curl your fingers, that's the direction of the field. So going around this loop, the field is going to be clockwise everywhere around the loop. And then dl, that's just small pieces of the loop. So dl there, dl there, and dl there. Now everywhere around here, B and dl are in the same direction. So if you think about that dot product B dot dl, you'd have B dl cosine 0 because it's a dot product. And of course, cosine 0 is 1, so we're just going to have B and dl. Now with that, we can pull the B out of the integral sign. Because if you look at B here, there, or there, they're all the same distance. So this B here, this is constant. And we know this is a current carrying wire, so the field is a constant value of mu sub 0 I over 2 pi r, where r is the distance to the center of the wire. So with that, our scary integral here becomes b line integral of dl. Well, now this is a line integral. We have the line integral of dl. Well, if you add up all the dl's going around the path here, well, that's just the length of the path, which is the circumference of the circle, so that's going to be 2 pi r. So we put all this together, we have the integral over the loop of b dot dl is going to be mu sub 0 I over 2 pi r, that's b, and the integral of dl, that's going to be 2 pi r. And obviously the 2 pi r's cancel out, and we get the integral of b dot dl equals mu sub 0 I. And that result right there, that's a statement of Ampere's law.
Here's the formal form of Ampere's law. It says the integral over the closed loop, that's what that little loop means, of b dot dl equals moink, which is mu sub 0 times current enclosed. And what you're going to do with Ampere's law, you're trying to find the magnetic field. So you're going to draw a closed loop or a closed path that's going to enclose the conductor that you're trying to find the field due to. And you're going to use properties of that loop, the field through that loop, to find B. And B is, of course, what you're solving for, so you're not going to substitute anything in for B. But what you will do, you're going to choose your Amperian path such that B is constant along that path. So this will always come out of the integral. And then you're just trying to find the line integral of dl. And what that means is you're adding up all the dl's along the path. So that just turns into the length of the path. And I have that word relevant here because you're only going to choose the parts of the path that have fields going through it. Now that's only going to be for one type of shape, which is a solenoid, where you're not just doing 2 pi r. 90% of the time when you're doing Ampere's law, you're drawing a circle for your Amperian path, and the integral of dl here, most of the time this is just 2 pi r. Mu sub 0, that's of course the magnetic permittivity of free space, which you know is 4 pi times 10 to the negative 7. And I'm drawing with a mouse, so I can't actually draw that well. And then I enclosed, that's the current enclosed by your Amperian path. Kind of like when we did Gauss's law, we did the charge enclosed by our Gaussian surface. This is the current that is inside of our Amperian path. And in physics C, there's a couple of key things you need to find the magnetic field for due to Ampere's law. That's going to be a current carrying wire, outside the wire and inside the wire, a solenoid, which is one of these, and then a toroid. And we'll also look at a coaxial cable.
Example A is asking to find the field around a long straight conductor, which basically means find a function for the magnetic field anywhere outside the conductor. So this is on the outside, some distance of r away. So let's go a distance of r away from the conductor. We want to find the magnetic field there. And we can find the magnetic field anywhere a distance r away. So what we're going to do is we're going to draw a path that's going to be a distance of r away, and it's going to have symmetry about the wire. Obviously, in this case, that's a circle. So we're going to draw this circle here. This circle is called our Amperian path. And this path here is a circle of radius r. And when you use Ampere's law, 90% of the time, unless you're doing a solenoid, you're going to have an Amperian path, which is a circle of radius r. So that's step one, is to actually choose an Amperian path, which is mostly the circle. And then step two is just to write Ampere's law. This is important because the AP exam does give you a point for just writing the Ampere's law. And there it is. The integral of the closed loop of b dot dl equals mu sub 0 I enclosed. So anywhere along this loop here, the field's going to be constant. So that comes out of the integral sign. And then let's look at the current enclosed. So if you think about anywhere along the circle, the current inside of it, it encloses the entire wire. So the current going through that circle is going to be the entire current. So this is I, and that's because our loop encloses all the current. And then the integral of dl, this is just the length of our path, which is just a circle. So we would have b times 2 pi r, the length of our path, circumference of the circle, equals mu sub 0 I. And our answer is hopefully not too surprising. Our answer is mu sub 0 I over 2 pi r, which you should recognize. That is the field due to a current carrying wire. Except for in this case, we derived it in 30 seconds, where with the Biot-Savart law, it took us quite a bit longer. So that's the field outside the conductor. Now let's go to example B, which is asking us to find a function for the field inside the conductor. So in this case, we want to find a function for the magnetic field at a distance of r, but now in this case, our r is smaller than big R, which is the radius of the entire conductor. So that's our Amperian path. It's still a circle with radius R, but now this is smaller than big R, the radius of the entire conductor. So here we go with Ampere's law. The integral over the closed loop of b dot dl equals mu sub 0 I enclosed. Okay. Now, the left side in this equation is going to be identical. B is b, that's what we're solving for. The integral of dl is going to be 2 pi r, and then mu sub 0 is mu sub 0. Now, the current enclosed, this is going to be JA, and we'll talk about what that J and that A means. So, J, this is called current density. Because as you go out in the wire, you're going to have current here, here, here. We're not enclosing all that current. We're only enclosing part of the current. So A, that's the area of our Amperian loop. And that's only based on the loop that we drew of radius little r. The current density here, that's based on the entire wire. So J, this is going to be the total current of the wire over the total cross-sectional area. And then A, that's only the area of our Amperian loop. So if we go to our next step here, we're going to have B, the integral of dl is 2 pi r, equals mu sub 0. And now J, so J is the total current of the wire, which is I, over the cross-sectional area of the entire wire, which is pi big R squared. Okay, so the density is always going to use the properties of the entire shape. So this is the total current over pi big R squared, which is the area of the entire wire. Now, this A here, this is just the area that we're enclosing. So that's our enclosed area, which is based on the radius of the Amperian loop. So that's going to be pi little r squared. And then we just solve from there. So this pi cancels there, one of the r's cancels, and your answer is a bit messier than it was for outside the wire, is mu sub 0 I little r over 2 pi big R squared. And that is the general formula for the magnetic field inside of a current carrying wire, but in physics C, you're going to have to be able to derive that.
Using the results from examples A and B together, we can graph the magnetic field as you go outwards, starting from the center of the wire, going outwards to find the magnetic field inside the wire and then outside the wire. So if you take this function here, for magnetic field inside the wire, when you get to the surface, you get mu sub 0 over 2 pi big R. That's the magnetic field here at the surface of the wire. And the function inside the wire, that's a linear function. So inside it would increase linearly like that. And then outside we would just have mu sub 0 over 2 pi r. So that function there would decrease. So that's the graph of the magnetic field strength as you go outwards from the center of the wire, going outside of the wire further and further away. It's going to decrease asymptotically out here. So the next shape we're going to use Ampere's law for is a solenoid. A solenoid is also called an electromagnet because most electromagnets are just solenoids. And what they are a bunch of loops of wire strung together. Now, when you just have a single wire, there is a magnetic field. It's not very strong. When you have a loop of wire, what's going to happen in a loop of wire is you're going to have your current, going around the wire. And if you use the right-hand rule to find the direction of the field, if you go here, using the right-hand rule, you get the fields into the page here, into the page here, into the page here, into the page here, into the page here. And basically what you get, because all these little currents are kind of having the same field, is these fields all add up and you get a pretty strong current when you have a loop of wire. And what a solenoid does is it takes many loops of wire. So if you look at the fields here, there's a very strong field within the loops of wire. There are some edge effects here. There's a very weak field outside, but it's not zero. But there's a very strong, pretty well-defined field here inside the wire. And that's kind of a picture of a solenoid. I have a bunch in my classroom that we use demos with, but of course we're not in the classroom right now.
Example C looks at the magnetic field due to a solenoid. This is the one case where Ampere's law is going to be a bit unique here. Every other time you use Ampere's law, your Amperian path is going to be a circle, at least in physics C. So in the left side of the equation, use Ampere's law, B dl, is going to be B times 2 pi r. That's the left side of the equation in Ampere's law pretty much always, except for right here when you have a solenoid. So we want to find the magnetic field due to the solenoid, and that's inside the solenoid. I can't draw, a circle here and have it be symmetric for the solenoid and make any sense. So in this case, your Amperian path is going to be a rectangle. And it's going to go through the center of the solenoid like that. And now it's going to have four sides. This is going to kind of be like Gauss's law when we had the cylinder. So we have the top side, the right side, the left side, and the bottom side. So when we use Ampere's law, we're going to do the integral of B dot dl, but we can't do it for the entire loop in general. We have to kind of do it piecewise. So we're going to have B dot dl for the left side, B dot dl for the bottom side, B dot dl for the right side, and B dot dl for the top side. And we'll go through and look through this loop. We'll look at what the field is and what dl is. So when you're in the middle of it, you have the field that way. On the left side, you kind of have field going out here. On the right side, you kind of have the field going to the left again. On the bottom, you really don't have any field. There is a little bit of field, but it's negligible. So we're going to look at B dot dl going around. On the bottom, there's no field, so B dot dl is going to be 0. Now let's look at both the left side and the right side. Okay, so let's say we have dl going this way. So let's look at the right side here. You have B and dl. dl is up, B is to the left. So if you have B dot dl, it's the dot product, so you have cosine of the angle between them. Well, they're perpendicular vectors. So since they're perpendicular, you get 0. So for the left side and the right side, you get that B dot dl is 0, and that's because those vectors are perpendicular. So when we use Ampere's law for a solenoid, we're only looking at the top, which is the actual part going through the solenoid. We only care about that dot product right there. And of course here, cosine 0, they're in the same direction. B's to the left, dl's to the left. So the cosine angle between them is 1. So we're going to apply B dot dl for the top side of our Amperian rectangle right there, equals mu sub 0 times I enclosed. Okay, now inside a solenoid, if you recall the picture, it's pretty much a uniform field. There are some edge effects, but we say those edge effects are negligible. So we're going to pull the B out of the integral sign and say that it's constant. And then let's look at our current enclosed. So every little turn here, you have a current in the solenoid. So if I have my current I have the current here, 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 for each loop. So if n's the number of loops, your current is going to be Ni, where n's the number of loops. Okay, so the field due to a solenoid then, you have B. This length here, that's the relevant length of the solenoid. So our Amperian path, that's only that side that goes through. So that's L, the length of the solenoid, and that's going to equal money, E sub 0 Ni. So then your field due to the solenoid is money over L. Now, in like the textbook, you might see it written as just simply money. It has a lowercase n. This n here, that's just called the loop density. That's just the number of loops per unit length. So that's the magnetic field due to a solenoid. That's the derivation of it. That is just simply a formula, but on the AP exam, this was actually on the AP exam last year, you have to know this derivation. So this derivation, you draw an Amperian rectangle, which I accidentally erased. You choose only the side of the rectangle that goes through the solenoid. All the other three sides are going to be negligible. And you're going to have B times L, the length of the solenoid, equals money. And there you go. That's the magnetic field due to a solenoid. It's written as money, or I guess some other people might say it's written as bunny.
All right, so our next shape is the toroid. The toroid is also called a toroidal solenoid because that's what it is. It's basically a solenoid, but instead of being just a long, straight thing of loops, it is wound into a little donut here. And there's a reason why we do this, and we'll look at it now. So here's the field due to a toroid. Now, if you look at the field due to a toroid, all the fields inside the toroid. There's no field whatsoever outside. So there's no fields here. These little magnetic filings are just scattered in no particular order. Same thing out here, but in the middle here, they are really well defined in a field. Comparing it to the solenoid, here's the solenoid again. You have some edge effects, you have a very weak field outside, whereas in the toroid, the entire field is concentrated within the loops of the toroid. On the left is just a picture of Michael Faraday's toroid. Michael Faraday actually used a toroid when he discovered Faraday's law. So here's example D. Example D is to find the magnetic field in various parts of the toroid. The first one is within the actual whole part of the donut that makes up the toroid. Then we're going to look at inside the actual toroid itself, which is where the field is actually strongest. And then we'll look at outside the entire thing. Okay, so part A is to find the field within the actual loop itself. Now this part is very, very easy. So we're going to draw an Amperian loop right here. I can't draw with the mouse, but there we go. It's of radius r. Don't think too hard about this one. This field is 0. So when we apply Ampere's law, we get B dot dl equals mu sub 0 times the current enclosed. The current enclosed, there's nothing here, is 0. So the field in this part right here is 0 because the current enclosed is 0. All right, so this is the actual part where we're going to do a little bit of Ampere's law. This is within the actual rings of the toroid. This is where the field is really strong. And we have a Amperian loop here. It's a circle of radius r, but now r was within the inner and outer radius of the toroid. So we are going to enclose some current. So here's our next step here. So our current enclosed is just like the solenoid, it's Ni, because if I have current going this way, I enclose it every single time. So I enclose the current, enclose the current, enclose the current. For every loop, I enclose that current. And of course, I have a Amperian circle. So the integral of dl for that is just the circumference, which is 2 pi r. And there's your answer. That is the magnetic field due to a toroid. And again, that is a general formula. Like this is always true inside of a toroid. But as a physics C student, you do have to know how to derive that. All right, now let's go outside the toroid. Now, if you remember the picture that I showed you, this again is going to be 0. Now, the reason why it's 0, well, let's look at the current enclosed. So again, we go integral B dot dl equals mu sub 0 times your current enclosed. So what's your current enclosed here? Well, on the inner and outer loop, just based on the nature of current flowing, they're going to be in opposite directions. So I have current into the page here, out of the page here. And every single, inner and outer part of the loop has a corresponding, so I have current into the page, there's a corresponding current out of the page. What you get here is the inner and outer loops cancel. So the current enclosed then is going to be 0. And the field outside the toroid in general is 0. So that's toroids. This region right here, field is 0. Out here it's 0. And here that's where you get that's where you're going to get your field. And that part's pretty simple as well, because then you just have B times 2 pi r for your Amperian loop equals Ni, because you have that current for each number of loops in that region there. So there we go with toroids. Our last thing we're going to find the field for with Ampere's law is the coaxial cable. Now what a coaxial cable is, you've seen these before. They're used a lot for audio equipment or for internet access, if you have internet, or of course you have internet, but for broadband internet access. And that's kind of a cross section of it. So what it has, we actually looked at one of these before when we were doing 9.2. We looked at the resistance of the insulating region here, because you don't want current flowing from conductor to conductor. But there's two conductors, an inner one and then an outer shell, and they run current in opposite directions. And we'll look at why that is in example E here. So example E is looking at a coaxial cable. So coaxial cables have current running in opposite directions. They are equal and opposite currents. And we'll look at why that is, and we'll go to the iPad and do example E.
Example E is to find the magnetic field due to coaxial cable. We're going to consider two regions. First, we're going to consider the region between this little insulating gap between. We're going to find the magnetic field right there. So we're going to draw an Amperian loop in this region. So here's our loop. It's in the region between them, between R1 and R2. So that's our Amperian loop. It's a circle with radius little r, which is between R1 and R2. And now we apply Ampere's law, and this is going to be pretty simple. And that's because, again, everywhere along this loop, wherever I go along the loop, the field's going to be constant. And then the current enclosed is just I, because we enclose all the current. The inner conductor has a current of I, so that's our current enclosed. And then we're using Ampere's law. It's not a solenoid, so the left side of the equation, our Amperian loop, is a circle. So the circumference of our Amperian circle is 2 pi little r. And the left side's always using little r. The left side's always using the radius of the Amperian loop, not of the actual conductor. Equals mu sub 0 I. And that's the answer. We're only enclosing one of the conductors, so we just get the magnetic field due to one conducting wire. Okay, so that's in between them. The next part here is going to look at, well, if you go outside the wire, what's the magnetic field there? This is when r is greater than r2. So here's our Amperian loop. That's step 1. Draw the Amperian loop. It has radius r, so that's our Amperian loop. It's a circle, radius r, where r is bigger than, this should say r3, which is the radius of the whole thing. And now we apply Ampere's law, and something pretty cool is going to happen here. So the left side, I mean, whatever, the left side is this. And then current enclosed. So look at our current enclosed. We enclose I1, or plus I, the current of the inner conductor. Then we have the current of the outer conductor, which a coaxial cable by definition runs these current in opposite directions for a purpose, and that's this purpose. So we get B times 2 pi r equals mu sub I. This is 0 times 0. So B is 0. And that's why you have a coaxial cable. There is no magnetic field outside of the coaxial cable. What that does, it protects the cable from outside interference. If you have other electromagnetic signals out there, it's not going to interfere with the signal inside here because there's no net magnetic field. So that's why your home internet is going to use a coaxial cable, because that's a signal you kind of want it to be protected. And there you go.
To sum up, this is Ampere's law, and it's used to find magnetic field due to conductors. We do so by first choosing a path that has relevant symmetry for the conductor. Again, it's almost always a circle, so we're almost always just going to do on the left side. This left side here is just going to be B times 2 pi r, with the exception of a solenoid, at least in physics C. There are more complex cases outside of physics C, equals mu sub 0 times the current enclosed, which the current enclosed is usually going to be I if you have a wire, Ni for a solenoid or a toroid, and then where you're going to screw up is where it's going to be Ji, which is if you're inside of a conductor. So be sure to try at least one example where you're doing a problem inside of a conductor. And yeah, that is Ampere's law.